Okay, good morning, everyone. I hope people are gradually getting over jet lag. We've heard several lectures yesterday around normality, and normality is, of course, related to uniform distribution. Uniform distribution is a very old subject. It's about almost exactly 100 years ago when it was first started seriously. But in the last few decades, there are properties that go beyond uniform distributions, which people look at, not so much in this community, and they want to make some propaganda for these properties. So just to quickly recall, uniform distribution of a sequence modulo 1 just means that if you look at the proportion of elements that lie in a given fixed interval, then that proportion tends to the relative length of the interval. That's what uniform distribution means. That's the definition, and I emphasize fixed intervals. The ones whose length does not depend on the number of points considered. So in particular, a uniformly distributed sequence has the mean distance, the average distance between its elements, 1 over the number of points, more or less by definition. So if you have 100 points in the unit interval, the average distance between them is 1 over 100 because they're roughly uniformly spread out. So an example that many people mentioned yesterday is if you take any real number and look at the fractional part of that number times 10 to the n, that sequence is uniformly distributed if and only if it is normal in base 10, meaning that any string of digits appears equally often in its base 10 expansion. And some numbers are normal, some numbers are not. Deciding normality is not easy usually, and we've discussed this yesterday. So some classical examples, if you take an irrational number and look at the fractional part of this linear form of alpha times n, when n varies, then these numbers are uniformly distributed in the unit interval. If alpha is 1, then of course the fractional part is 0, so it's not uniformly distributed. A more serious example is if you take an irrational number and multiply it not by n, but by n squared, then Weil showed that these fractional parts are uniformly distributed. And likewise, if you replace n squared by any integer coefficients polynomial, any polynomial where at least one of the coefficients is irrational. Another example is, instead of taking a polynomial, take square root of an integer, and then as you vary over all integers and look at the fractional parts, you still get a sequence which is uniformly distributed. Not all sequences are uniformly distributed, of course. Another classical example, if you take the fractional parts of log n, then these are not uniformly distributed. So all this can be found in the first few pages of your favorite textbook on uniform distribution. But most sequences, in some sense, are uniformly distributed. Here's a classical result. If you take any sequence of distinct integers and multiply them by your favorite number, real number, then for almost all choices of this favorite real number, this has stopped working, that sequence is uniformly distributed. Okay, so this is another classical result. Okay, so we want to go beyond uniform distribution, so that means looking at other statistics of this sequence. And here are 3 statistics I want to examine. The distribution of gaps between nearest neighbor elements, the distribution of all gaps between elements, and the minimal gap of the first n elements. So I will define them carefully here. Okay, so the distribution of nearest neighbor gaps. In all the sequences I've given to you, the way you lay them out, there's no ordering. They don't come ordered. Now what you need to do is order them. This is a non-trivial operation. Take your elements, like the fractional part of alpha times n squared, generate the first 1,000 of these using Mathematica or something, order them, and then look at the gaps between nearest neighbors. Normalize these gaps so that on average they are 1. This is a normalization just so that I can do statistics on a macroscopic quantity. And then look at the distribution of this random quantities, or quantities that are not random if you put down your favorite sequence, but you pretend that they are random and try to study the probability distribution function of these random quantities. So for instance, you would ask how many of these normalized nearest neighbor gaps are less than 10, and the proportion of these you hope tends to a limit, and that limit has a density, you hope, and that density is called the level spacing distribution. Again, you have to hope that it exists and that you can figure out what it is. So that's called the level spacing distribution. So this is the definition. I just want to make sure we understand the definition. Now, I'm going to show you a few examples of, it's very difficult to compute in general, but very easy to do numerics on, which is what makes it fun. But before you try to prove something or to experiment on something, it's good to have some models in mind of what to expect. And there are 3 main models that I want to discuss. The first one is a trivial one, so it's called a picket fence in the physics literature. You just take, for instance, numbers which are exactly equally spaced. So the sequence, just the integers, for instance. So the integers have mean spacing 1, but they have exact spacing 1. They are spaced 1 apart from each other. The nearest neighbor gaps are always 1. Then the level spacing distribution is kind of trivial. It's like a delta function. Whatever it is, it's not interesting. There are examples in nature which are like that, but we are not going to discuss those. The next, much more interesting model is if you imagine your sequence is completely random in the sense that you take in 100 points which are uniform in the unit interval and independent. Then the question is, what is the, let's say, expected or almost sure level spacing distribution? Again, to compute it, you have to order these points which are laid down at random independently. They don't come ordered. So let's see this and then go back. So you take these points, then form the so-called order statistics. Look at the nearest neighbor gaps, normalized to be 1 on average. And then the result, it's a classical result, that these normalized gaps are identically distributed, and each of them has, in the limit, an exponential density. So that's the model we are trying to shoot for. Another model is, instead of thinking that the points are random, you think they come from another kind of random process, and the ones which occur in life, in nature, are eigenvalues of random matrices. So there are many flavors of random matrix theory. So you take your favorite random matrix, I'll show you an example in a second, compute the eigenvalues. Let's say they are real. If the matrix is real symmetric, then they are real. Order them and play this game of nearest neighbor gaps. The eigenvalues are no longer independent. They are random, but no longer independent, or at least there's no reason that they be independent, and so there's a non-trivial computation to be done. Let me just show you this plot. So the green line is the exponential distribution, which is what comes from independent levels. And that's the thing that you usually see in the kind of concrete examples we've seen here. If you play this game for random matrices, you typically see something like this red curve. And the difference between them, beside having different shapes, is that this red curve vanishes at the origin. That's interpreted as a level repulsion. That these eigenvalues want to stay far from each other typically. What? Level repulsion. It's physics jargon, but if you take random points, there's lots there's a big chance that they cluster together. And to make up for it, there are big chances that they are far apart from each other. While, as it turns out, for eigenvalues of random matrices, they are much more rigid. They don't want to cluster together. And this is the explanation. The distribution vanishes at the origin. How it vanishes and so on, that's a different issue. So let me just show you three models. You can take random symmetric matrices where the matrix elements are independent up to symmetry. That's one kind of distribution. I didn't say what is the distribution of a particular matrix element. It turns out not to matter. This is called the Gaussian orthogonal ensemble. Then you can take Hermitian matrices, or my favorite example is unitary matrices. The unitary group has a canonical probability measure called Haar measure. And if you choose the matrix random with respect to that probability measure, you get a certain distribution on the eigenvalues. They are not independent, but it looks like this red plot that I showed you. Okay? And the reason that people started looking at random matrix theory is because they are trying to understand the gaps in the energy spectrum and the energy levels of complex nuclei like uranium and so on. And here you see some pictures of the empirical distribution that you get from your favorite heavy atom. As compared to these solid curves, this curve would be the Poisson ensemble, the independent levels, and that's clearly not the right thing. Well, this thing would be the GOE curve, which looks okay. This is not a theorem. This is not numerics, it's experiments. But that's why you would want to see them. Okay, now, yes. Yes, so the Poisson thing, the exponential distribution decays exponentially. These random matrix distribution, GOE, they decay, they have a Gaussian decay. So they decay very fast. But that, of course, is harder to see experimentally because you have to go way out into the tail of the distribution. The origin is much easier to pick up. So here, you typically only have a few dozens of levels. You're going to see the repulsion, but you can't tell anything about the tail way out. Now, as I kept saying, it's a non-trivial operation to order the points. So the level spacing distribution analytically is very hard to get your hands at, even though experimentally or numerically it's obvious what you do. So what people do instead often is look at what is essentially the second moment of this distribution, and it's called the pair correlation function. And what it is you look at the gaps between any 2 points, so you don't have to order them anymore. So you take your points, normalize them so the average distance is 1, and ask how many pairs of points there are whose distance is at most 10. So there are, if you take n points, there are n squared pairs roughly. But if they are spaced one apart, if you choose one point, at most 3 points which are a distance one apart, and if you now vary over all points, you expect roughly order n such points, so you divide by n. Good, I remembered to say this. And you hope that there is a limit. And when there is a limit, it should have a density, and that's called the pair correlation function. And that's a quantity that is analytically easier to compute, and it's essentially the second moment of the level spacing distribution. So in the random models, for instance, if you take the uncorrelated levels, it turns out that this density is just 1. If you think about it, it's clear why it's 1. If you take unitary matrices or emission matrices, then there's a different, it's 1 minus something. And the picture of this looks like this. So 1 is this green line, and then the random matrix theory guys vanish at the origin. That's this level repulsion. Okay, so that's a feature you may want to pick up. Okay, so we have the level spacing distribution, which is easy to do numerically. We have the pair correlation function, which is a little harder to do numerically, but still very possible, but it's more tractable analytically, and it does distinguish level repulsion from level clustering, so that's a good thing. Okay, so now let's do numerics. Instead of experiments, let's do numeric. Let's look at our first favorite sequence, alpha n squared, the fractional parts of alpha n squared. So you take Mathematica, take your favorite alpha. My favorite alpha is, let's say, square root of 2. Generate 2,000 points, order them, compute, do the histogram. That looks like Poisson. If I'm a betting man, I would say this is Poisson. So you can stop listening now and try to prove it. I don't know how to prove it, but it's my problem. But this is pretty convincing to me. So I've looked at this a few years ago, I should say, and after doing some numerics, it's easy to conjecture that this would be the answer. Of course, if you take alpha to be 1, the fractional parts are all 0, you're not going to get anything. If you take alpha to be rational, you're not going to get anything interesting either. So you don't want alpha to be rational. And then there are other traps here. So we know that if alpha is irrational, then this sequence is uniformly distributed. But this is not the case for this level, for these finite statistics. So if alpha is a number that thinks it's rational, like the one we saw yesterday of a Liouville number, then you will not get anything nice. This is easy to prove. The bad things are easy to prove. But we believe that if alpha is, let's say, an algebraic number or anything which is Diophantine in the proper definition, then the level spacing distribution will be Poissonian. But that's a conjecture. We, at this point, don't know how to do it. It's work I did with Peter Sarnak and Alexandru Zaharescu a while ago. So Diophantine or badly approximable means that you cannot approximate it too well by rationals in this sense. I expect most people know this here. So the level spacing distribution I don't know how to touch. What we can do something about is the pair correlation function. And for the pair correlation function, we can show that for almost all alpha, you get the result that's consistent with this picture. But I want to emphasize, I don't know how to do it for individual alpha. It's a metric result. So, and I don't know how to do this picture for almost all alpha either. Now, instead of alpha n squared, you can look at alpha times any polynomial with integer coefficients of higher degree. I emphasize higher degree, meaning 2 or more. And then you'll get the same result, that almost surely the pair correlation function is Poissonian. I will show you the case of linear polynomials, alpha n later, in a couple of slides. Okay, so I was trying to do square root of 2 times n squared, and couldn't do it, and then in despair I twisted the page, and instead of n squared I looked at 2 to the n, which is of course infinitely worse because I can't do any example, I can't show that any example that I want to look at is uniformly distributed, let alone finite statistics. But it turns out that the metric theory here is easier, and you can show that almost surely the level spacing distribution is Poissonian. And the way we do it is we compute essentially all moments of this distribution. So the second moment is a pair correlation, then the higher moments I call n-level correlations, and some kind of work to do, and you do it, and it works out. So almost surely, the level spacing distribution and the pair correlation and 3-level correlation and so on for alpha times 2 to the n is Poissonian. Instead of 2 to the n, you can also do 3 to the n, or 5 to the n, or your favorite number, or any Lacunary sequence in the suitable sense. Now, of course, we don't know how to do this for any individual alpha because we don't know how to do any interesting individual alpha is uniformly distributed. And the examples that were mentioned here yesterday, where you can show that a number is, say, normal in base 2 or base 10, it turns out do not have this property. They're not random at this level, which, again, is hardly surprising. So Champernowne's constants and other examples do not have this property. They don't look random from the point of view of the distribution of nearest neighbor gaps. So this was only observed recently because this subject sort of languished. That was 20 years ago. I was trying to convince the uniform distribution community to look at this, and it was like a voice in the wilderness. So they turned to other things, and then the way these things happen 20 years later, people start looking at it now. So there will be lots of results from the last couple of years. Okay, so let's go back to linear polynomials. So if you look at alpha times n, the Kronecker sequence, that is not random. Even though it's easy to show that it's uniformly distributed, it's not random. So this was known to mathematicians many, many years ago, but it was rediscovered by the physics community when they were looking at this, not in this language, they were looking at so-called coupled harmonic, independent harmonic oscillators. They were doing numerics and were getting very, very strange results, not at all like the ones we saw before. And the explanation for this is an old result called the three-gap theorem that maybe someone will discuss this week, that says if you look at the sequence alpha times n, the fractional part, and look at the first 100 levels, there are only 3 distinct nearest neighbor gaps. If you look at the first 200 levels, there are only 3 distinct gaps, but they are different than the ones before, and so on. It's an old theorem. If you haven't seen it, stop listening now and try to prove it. It's elementary, but I can never do it correctly. Okay, so in any case, there's no limiting level spacing distribution. So everywhere I sort of assume that there is a limit. It's not the case here. Another example. So I was talking to Igor yesterday, and he was saying everything is Poisson. This is not true. So if you take the fractional part of square root of n, again, this is uniformly distributed. The level spacing distribution looks like this. It's flat, complete, it's a straight line at the origin. And then it goes down a bit and then goes down differently. So there's a theorem here. So this was discovered experimentally by Poisson in the 1990s and was proved by Noah Melkis and Kurt McMullen early 2000s. There is a limiting level spacing distribution, but it's not that of random numbers. So there's a formula. It's a piecewise analytic function at the origin between 0 and a half. It's completely flat, and then it has one shape up to 2 and another shape up to beyond 2. It is what it is. It comes from push down of some algebraic measure in homogeneous dynamics, as it turns out. It has to do with primitive lattice points. No, not continued fractions. They relate this question to distribution of primitive lattice points in some sense. They use Siegel's mean value theorem. Yeah, so if you look at the number of primitive lattice points in a ball, you get one. Yeah, so that's the origin, and then the explicit formulas, it's not a most serious thing, but they're just long, but the explicit formulas for what happens here and what happens here, but it's not smooth at these points. So this was discovered a while ago, published 15 years ago. And then a few years ago, Jens Markloff with Daniel Elbaz and Ilya Vinogradov looked more carefully at this distribution. It turns out that the second moment of this distribution is Poissonian. Not because it's Poissonian, just it's because the same function. So the pair correlation function for this sequence is like that of random numbers, but it's a it's completely misleading. This is not a random sequence. Okay? Now you may think, all right, how about we jiggle this example and multiply square root of 2 by the favorite irrational number. And this is the picture that you have. This is not a theorem. This is a numerical experiment which I ran on my computer yesterday in 1 second, but this is another thing. If you replace alpha square root of n by alpha times square root of n, it seems that the level spacing distribution changes dramatically and it moves back to the random case. Okay, so you don't want alpha to be rational. For instance, you don't want alpha to be 1. That's this picture. If alpha is 2, you move the 2 back in here, and you get square root of 4n, and that would behave like this. So, okay, so cube root of 2. What is the? Sorry, I didn't. Definition of Diophantine is that it cannot be approximated too well by rationals. For instance, algebraic, but most numbers are Diophantine. Maybe I called it badly approximable. I never know exactly the terminology to use, but it's clear. Right, so here I took cube root of 2. Or you can take pi, and you'll get the same picture numerically. You go. It's just I meant what I wrote. So I don't want this to be irrational. This, okay, I should have called this one of them beta and the other alpha. There's a reason why so if you take square root of an irrational number, which means any number which is that you can't put into the square root then that would be the conjecture. So as long as you don't do anything stupid to get back into this picture, and stupid means take this number to be rational, or I don't want to think about Liouville numbers at this point. I'm sure I will not get anything interesting. Then I believe you'll get this picture. But I don't know how to prove it. Now, what is special about square root of the square root? If you replace square root by cube root, you seem to be back into Poisson. I don't have any theorem here. I'm just showing you the numerics. Okay, so I have nothing to say about it except go and prove it. Let's move back to pair correlation. So as I said, this theory was sort of dormant for a couple of decades until 2 or so years ago, and people started looking at it, and they took the arguments that we had and encapsulated them in a very nice and useful fashion. So for instance, if I give you a sequence of integers and look at alpha times this integer and want to prove that its pair correlation is Poissonian, then there's a simple criterion available to tell you whether or not the pair correlation is Poissonian, and that has to do with the so-called additive energy of the sequence. The definition of additive energy is you look at solutions of this equation in elements of the sequence. Now, if the A's are distinct integers and they give you K, L, and M, then A of n is automatically determined. There's at most one solution. So the additive energy is at most n cubed. And if I take the diagonal solutions, K equals M and L equals N, that's two pairs of numbers that for sure solve this equation, so there's at least n squared. So the additive energy is always between n squared and n cubed. And the criterion is, so it evolved over 2 years or so, that if you have almost any non-trivial upper bound on the additive energy, so if you take the trivial upper bound of n cubed and divide it by, and replace it by n cubed over some power of log, the power has to be bigger than 1. It's not clear what the constant, what the power is. If you have this upper bound on the additive energy, then automatically, for almost surely, the pair correlation function of alpha an would be Poissonian. So it's a criterion that's easy to check. It doesn't tell you anything about specific alpha. It's a metric theorem. And the counterexample that you actually need a power bigger than 1 is the sequence of primes. So this was a paper of Aled Walker from a year ago or so. So for the sequence of primes, it turns out that for almost all alpha times prime, even though it's uniformly distributed, it does not have Poissonian pair correlation. This is one fact. And another fact is that the additive energy of the primes is roughly n cubed over log n. So it doesn't contradict the theorem. It just says that you cannot replace log n to a big power by little of n cubed. Okay, so all these examples were Poisson, or things that look like Poisson. Let me show you a natural example which started this theory for me, where the level spacing distribution is definitely not Poisson, and that's the Riemann zero. So this is no longer a sequence mod 1, it's a sequence of, you look at the imaginary parts of the Riemann zeros. This, we believe, are real numbers. No, sorry. Let me formulate this properly. I was going too fast. So for people who are still asleep, here's the Riemann zeta function. One of the interesting things about the Riemann zeta function is that it has lots of zeros. So if you look at the zeros of the Riemann zeta functions whose imaginary parts lie in a big box, up to a certain height. So you look at them in a big box. I didn't plan to do the details here. So here's the S-plane. This would be half, this would be 0, this would be 1. So there's some trivial zeros of the Riemann zeta function here. They're not interesting. And then Riemann found some guys here. The first one is at height roughly 14. And if you look at the number of zeros in a box of size t, well, they're all here. Nobody's ever seen a zero off the line, so they're all here. Then there's about, up to t, there's about t log t zeros. So the mean gap between them is about 1 over log t. They become very, very dense. And as I said, they're all supposed to be on this critical line. And they become dense, so the mean spacing, this should be 1 over log t, not log t. And you can try to compute the level spacing or pair correlation. And Montgomery, in the early 1970s, computed what is now called the pair correlation. He didn't realize it was called that. And he got this answer. So this, okay, no, this is not a theorem. This is a conjecture. He got something weaker, which I don't want to tell you. He got this answer, didn't know what to do with this, and then showed it to someone who had seen this before, and he told him, this is the same answer as you'd get if you were looking at eigenvalues of random emission matrices. And once you know what to look for, you can do experiments, and this is the scatter plot is the empirical thing. You do 100,000, the first 100,000 zeros or so. The statistics here converge very slowly. And it looks like it matches the solid curve, which is what you would get from this thing. Once you know this, you can do the level spacing distribution. And here is 100,000 zeros, but you have to go a little far up. And they definitely don't have Poisson level spacing distribution, but they have something else, which is this random matrix theory feature. So these are not exactly theorems, but there's a lot of evidence toward it, so we know essentially all moments in some weak sense that I don't want to discuss. So this is a naturally occurring sequence where you have a level spacing distribution. It's not Poissonian, but it is some definite random thing. But the randomness comes like from eigenvalues of a random matrix. You may ask, what is the matrix? That I don't know. Okay, so the last quantity that I want to discuss is a different quantity. Instead of looking at the typical gap between nearest neighbors, let's look at the smallest gap. So I have n points in the unit interval. let's say they are uniformly distributed, so the average gap is 1 over n. We said the typical gap will have an exponential distribution after you normalize it. It's still of size 1 over n. What is the size of the smallest gap? Now, this is an exercise. If I give you 1,000 points, random points in the unit interval, what is the size of the smallest gap? The average gap is 1 over 1,000. Turns out that the smallest gap is size 1 over 1,000 squared. This is an exercise. It's called the birthday paradox. That's how you solve it. So the smallest gap is much, much smaller than the typical gap for a random sequence. You may ask, what is the behavior if you look at eigenvalues of random matrices? And it turns out that for those, the minimal gap is actually bigger than what it is for uncorrelated levels. How big depends on the flavor of random matrix theory you're using. For random unitary or emission matrices, it's of size 1 over n to the 4/3. Again, you compare it to 1 over n squared, which is for random levels, 1 over n, which is the typical gap. And for random symmetric real symmetric matrices, it is slightly smaller. This was proved only last year, by the way. So it's not an easy thing. So this is the statistics I want to investigate for our favorite sequences. And here is one result. If you take any sequence of distinct integers and look at alpha times that sequence, so we know that it is almost surely uniformly distributed. We had this additive energy criterion that says if the additive energy is anything slightly less than the trivial upper bound, then the pair correlation function would almost surely be Poissonian. And you can give an additive energy criterion for the typical gap to be consistent, at least with Poisson statistics, to be roughly of size 1 over n squared. And the criterion is that the additive energy grows, so the trivial lower bound is n squared, the trivial upper bound is n cubed. If it grows not much more than n squared, not much more than the lower bound, that's sufficient to give you that the minimal gap is consistent with Poisson statistic. Then you can ask, are there examples of sequences where I can prove this additive energy bound? And it turns out to be easy. If you take polynomial sequences or Lacunary sequences, you can give, 20 years ago, I gave this bound because this is how I proved anything about pair correlation. So you get for free, essentially, once you have this criterion, that the minimal gap almost surely for your favorite sequences is Poissonian. On the other hand, if you look at the sequence of primes, so alpha times p is almost surely uniformly distributed. As I told you, it is almost surely not got the right pair correlation. And here too, you can show that almost surely the minimal gap is actually very, very big. So the average gap of n elements in the unit interval is 1 over n. For alpha times, fractional part of alpha times primes, it's almost surely essentially 1 over n. So they are very rigid from this point of view, not random. Okay, so this is another statistic that you can happily play with. So let me just close with some homework. So I showed you lots of pictures. They're not particularly beautiful, but they're easy to generate. So take any of these pictures and try to prove something about them. So for instance, to show that square root of 2 times n squared is Poisson pair correlation. Or take square root n and multiply it by something reasonable like cube root of 2, shall compute its pair correlation or level spacing distribution or so on. Or say something about almost sure pair correlation here. I had a slide with a theorem, which I generated in half an hour, and then an hour later it vanished, the slide and the theorem. So I left it as a question. And you can also ask questions about minimal spacings. Okay, thank you. No. All concrete examples. This is not true. People have examined some concrete example and showed that they are not Poissonian. I expect this to be true for all examples you can think of, but for instance, someone mentioned yesterday this concatenating squares or concatenating primes. I don't know if people have examined this. It's worth doing. If I'm a betting man, I will bet that they are not Poissonian. And it can be checked.
Polynomial of the degree greater than 1. If you know that if at least one of the coefficients greater than 0 is irrational, then it's a uniform distribution for the 1. How is this? And so for almost all the polynomials of the degree e, therefore they
So if you take a fixed polynomial of higher degree with integer coefficients and multiply it by alpha, then for almost all alpha, the pair correlation is Poissonian. Now you want to vary several coefficients. I expect that something like this would be true. I don't think it's been done. You probably have to be a little careful how you formulate it. If you're careful, I think it is something one can try to do. I expect this to be doable. Conjecture means I tried and failed. Tried hard and failed. Okay. No, as far as I know, it's not been done. So you can try, you can think of varying few coefficients. And if you vary a lot of coefficients, you may be able to show not only the pair correlation, but higher correlations, a few higher correlations are Poissonian. So that would be interesting to do for sure. On the discrepancy? I don't know a formal implication. On the other way, but this, this level spacing pair correlation deal with behavior in intervals of size 1 over n. Discrepancy tells you something about shrinking intervals. A bound on discrepancy says uniform distribution on shrinking intervals where the rate of shrinking has to do with the discrepancy. This is what discrepancy is used for. The examples I showed you of alpha times n has low discrepancy and don't have Poisson level spacing. I don't know a formal implication, but here's something to try to do. As Veronica suggested. If you have a sequence with very low big alpha n, what is the? No, alpha times 2 to the n, that's low discrepancy or high discrepancy? What is?
How much is known about that?
I don't think, as I said, this subject was dormant in your community. Not dormant, it didn't live until the last 2 years. So people haven't looked at this. But it may well be the case that our results that says if you have Poissonian pair correlation, then the discrepancy cannot be too, what is small or big?
Not the small,
Alpha n is a big or small discrepancy? Square root 2. Small, and I don't know the adjective to use here. So sequences with low discrepancy maybe. No, so Poisson might mean small discrepancy. There might be some implication, which is what you're asking. I would be careful. So the example we had of fractional part of square root n. One knows a bound for this discrepancy. I don't remember what it is, but you use Weil sums to prove this theorem. So there is a bound in the discrepancy, but it's not Poissonian. But the pair correlation is Poissonian. The level spacing is not pair correlation. So there might be some implication one way or the other. I don't know it. I don't know it. No, I don't think that anyone has looked at this, but it's certainly an interesting question. Again, alpha times what? No, I don't know that it's not possible. I know that it has measure 0, but I don't know that it's... So there was a theorem yesterday where the exceptions were only countable. I don't know such a result, and I'm sure it's false, by the way. So Liouville numbers are bad. This I know. So, sorry. So I think I know the answer. It's not countable because Liouville numbers are not countable. But you can ask for a bound in the house of dimension or something like this. This I don't know. So if you look at alpha n squared, then it's almost surely, in the sense of measure theory, the pair correlation is Poissonian. Badly approximable probably means not Liouville. I don't know the definition of Liouville. Meaning it's a matter of, I know a Liouville number when I see it, but when you try to give me a definition, I will. So I think what I want is alpha. This notion of badly approximable. So whether you want to put C anything bigger than 2 or any C is a matter of taste, I believe. In all results, it functions as the same thing. For such again, because they all measure 1, the question that would be interesting is the set to give an upper bound on the house of dimension of the set of exceptions. No. The dimension goes to 1, yeah. So the exceptional set includes Liouville numbers, which are numbers which don't satisfy this, but they may include more numbers. I don't know what are the exceptions. I don't know I'm not saying that only Liouville numbers are exceptions. I'm saying Liouville numbers are definitely exceptions. But there is probably maybe a bigger set. I don't know what it is. One way to try to measure it is to bound the house of dimension. Maybe it's 0. I don't know.
one of our outcome is therefore relating it possibly. So do you have a concrete example of outcome?
No. I mean, I have several that I showed you pictures. I don't know how to prove them. No example proved. Okay, thank you.